back.
All right, thank you. All right, so today I want to talk about some time domain hydrodynamic modeling for floating bodies. There's a lot of familiar faces in here, so I'm probably not going to tell you anything you don't already know. So feel free to take a nap or leave or what have you, but there's probably going to be some redundant stuff here. I think a lot of you already know this. So let's get into it. Quick outline here. I want to talk about why and how we want to model in the time domain, some of the advantages associated with that. And then specifically for this talk, I want to define a few terms: fluid structure interaction, Hydra Elasticity, and weak and strong coupling within the hydroelastic modeling realm. And then present a few Fsi tools and examples, and then at least one hydroelastic tool and an example. So first of all, time domain simulation, again, I think we all know this. There's a lot of limitations when you use a frequency domain. Everything has to be linearized, time invariant, obviously, by definition. And specifically when we're considering wave energy converters, there's usually poor performance around resonance. And that's due to the fact that you have small perturbations around the free surface and small amplitude motions. And so how do we do this? Well, how do we solve in the time domain? Well, one of the ways, there's a couple of ways I'll talk about today, is by solving the boundary value problem. And you can do that either through boundary element method, BEM, and so then the convolution of the impulse response functions to get back into the time domain, or directly through a finite element method. And so that's the two different areas that I'll talk about today. So first of all, let me define fluid structure interaction specifically for this. I mean, it depends on who you talk to and when you talk to them and what you're talking about when it comes to what is the definition for FSI. Specifically here, I want to talk about just a rigid body boundary condition such that the fluid responds to interacting with the water and the water responds to interacting with the fluid. Did I say that backwards? The body interacts with the fluid interacts with the body. Nothing spectacular here. Now, some of the solution formulations for this, again, BM and FEM. You see CPTs moving there from Stephen Zhang's MS thesis, and that's in the boundary element method. And this is a TLP from a finite element method that I'll talk about a little bit more later. Okay. So now let me define hydroelasticity, really distinguishing between those two different terms. In this case, there's a flexible body boundary condition. That is that the actual structure of the body responds to the fluid forcing. There's deformation in the body. And there's a couple different ways of coupling these two different domains, the fluid domain and the rigid body, the flexible body domain. And that's through weak coupling or strong coupling. An example of this, and this ties more directly into my actual research. By the way, my actual research is not in wave energy per se. It's more on surface effect shifts, and that'll become apparent as we get to the end. But here in this experiment, we have a free surface flowing from left to right. And you can think of this as, I should have brought a sheet of paper. It's a sheet of paper, but it's basically a piece of fabric that protrudes through the free surface, and then as a flow comes from left to right, that flexible structure, very flexible structure, gets folded up under due to the interaction with the free surface. I think I'm good for now. So that's from an experiment at a Navy facility in Memphis, Tennessee, here. And then this is a simulation of the full hydroelastic problem, coupling the fluid boundary and the structural model, a highly nonlinear, highly deformed structural model. Okay. So now let me define weak and strong coupling. I should say there's a much better reference in the room for this definition than me, but I'll point to him if there's any questions that come up about it. But again, the definitions of this type of coupling depends on who you talk to and the type of situation you're talking to. So I want to clearly define what I'm trying to say here. With weak coupling, in a simulation that I'll show in just a little bit, for each time step, only one domain is solved. So, for example, in this case, the fluid domain is solved, then the pressure or stress is communicated over to the structural domain. The structural model is solved for deformations and positions, and then fed back into the fluid model, et cetera, et cetera. So that's just a weak coupling scheme. A strong coupling scheme is for each time step, both domains are solved iteratively, and so they converge to a solution given some tolerance that you're aiming for. And so then as we go march forward in time, for each time step, that same iterative technique is used. Okay, so that's what I mean by the strong coupling procedure. So now let's talk briefly about some of the Fsi tools that have been used. Of course, Wayman is sort of the grandfather of them all. Boundary element method, and can support some linearized forcing. It's pretty limited in that case. And then there's several people in the room who are very familiar, much more familiar with Aqua than I am. But again, it's boundary element, and it has a time domain module that can be used to add in some nonlinear forcing, such as damping. But that damping term modifies the equations of motion such that you can have some viscous drag in the time domain, or that viscous drag could be proportional to the power takeoff system, or some other type of viscous drag external forcing that you have in the system. And that still has to be tuned. It still has to be optimized for your particular case. At least that's the way I understand it. So today what I want to talk about is something new, two different tools here. One has a sort of a strange name, TD_XXX, which can be read as time domain fill in the blank. And this is really a suite of MATLAB scripts that are used to take in the impulse response functions generated by WAMIT or Aqua, and then you can have user-defined nonlinear time domain external forcing to help model your system. I purposely put in this picture here from Kelly Rule's thesis because at the heart of all of this, the solution technique that Kelly used is exactly what TDXXX is using. It's just packaged differently in MATLAB. So I mean, really, that's kind of the gist of it. The theme of the day might be actually, I'm going to tell you things that were done 2 years ago by other people, but packaged differently, really and truly. The other tool I want to talk about is Compass TDYN, specifically what they call the CFEM module. It's a finite element model, and what's nice about it is that in the environment, native to the environment, is a structural analysis package as well. So as you solve the FEM fluid problem, you can readily export that data and then solve the structural model just a few clicks of a button, really. Okay, so some of the background for TDXX was developed in MBARI, the Monterey Bay Aquarium Research Institute, by Dr. Andrew Hamilton. And this was an in-house tool that he used for a couple years for designing buoys and mooring systems. When MBARI was part of the Ocean Observing Initiative, groundwork, when they were first trying to figure out how the buoys needed to be designed, he used this tool to help design some of those systems. And then there was a DARPA project called the Renewable at Sea Power Project, and this was kind of a neat little project. The goal was to distribute sensor nodes in the ocean environment for environmental monitoring, or ISR, intelligence, surveillance, reconnaissance missions. And one of the requirements is that each of these systems had to loiter in a specific region, so it had to have some maneuverability, and it had to generate its own power through renewable energy sources. And so obviously one of the methods of doing this is to use a wave energy type of buoy to power these sensors and maneuvering thrusters or what have you, whatever was on it. So the workflow here for TDXX is fairly basic. Define the environmental conditions, so wave and wind conditions. Define the size and shape of some of the objects the bodies that you have in your domain that you're interested in. And the description of the forces here is very important. The connection between the bodies is very important because, that's how the external forcing for each body is defined. I'm not going into too much detail. There's a manual available. It's very readable, and you can figure it out pretty quickly how it's been used. The numerical model here really is just that convolution of the impulse response functions with the time domain forcing. That's really the heart of it all. That's about it. And then the outputs here are the motion time histories and force time histories. So now let me really quickly give you a demonstration of how this could be used. This buoy up here, on the top left, is a small buoy floating at the surface. It's connected through a tether that has some spring constant and damping in it. And it's connected to a damping plate down the bottom. Now this plate is free to swing back and forth. And this damping and swing constant is not just a function of the dynamics of the tether, but also could be the dynamics of the PTO also. Okay. And then this is one of the examples that's distributed with the software. It's a public domain collection of scripts, like I mentioned. But then I wrote a real simple visualization to go on top of that to help me try to interpret some of the results from this program. So let me switch over. So first what we'll see is you have the buoy up there in green, you see the free surface, the tether, the damping plate. Now, I should say real quickly that some of the visualization is not very precise. There's actually a bridle attaching the tether to the damping plate, but let's just pretend it's that right now. And then we see the time histories of huge sway and roll. And in this case, the wave is going directly into the board. So this is a long-crested monochromatic wave. Okay. And you'll see the red line here march across as the motions of the buoy. That's not what was supposed to happen. All right. Technical difficulties. I already ran the simulation, which it took 30 or 45 seconds or so of computation time for a 120-second simulation. So, why is this not working? Right. Okay, well, if it was working, what you would see is the buoy heaving up and down, the damping plate heaving up and down as well, and the elongation of the tether in between. Josh has seen this. He knows it works. I promise.
How do you define your geometry in this? Is it?
Well, yeah.
Can you do it in aqua?
Exactly. The geometry that is important is defined in either Wayman or Aqua.
Okay.
Because then that gives you the impulse response function. Actually, what's being read in here is the frequency domain response, the RAOs, from either Wayman or Aqua, not necessarily the IRFs. So, and the geometry that I'm using here basically is just for the visualization. Now, that's true for the buoy. For the damping plate, the geometry matters quite a bit because there isn't a wave excitation force on that body, there's only a drag force. And so then the orbital velocities matter, and so then the planetform area of that body matters quite a bit. Okay, so what should I do now? This is where we're starting. Alright, well I guess I'll just have to skip it. The other simulation, or the other degrees of freedom that I was going to show you is this example here where the wave was propagating right to left. And you can see the really large amplitude oscillations in the lower body down here. I also added a few small flags here, incidents of overtopping or incidents of breaching on the buoy. If either one of those happens, you really start having to question your Wayman and Aqua assumptions at that point. Simple. Okay, so now let's talk about the CFEM simulation. And first we'll start talking about the fluid domain theory, which everyone has seen before, I'm sure. Viscosity, rotational, linearized free surface, and velocity components. Thus, the governing equation in the domain is the Laplace. Boundary conditions, I think you've all seen before. Dynamic boundary condition on the free surface and kinematic boundary condition on the free surface, the first two equations. Third equation is the body, rigid body boundary condition, and then the bottom boundary condition, kinematic bottom boundary condition is the last equation. And then this is all solved with FEM. I think I've said that 3 times now. So we'll go through a real quick FSI example of how CFEM can give you really nice results, especially for the structural modeling side of it. We'll consider a commercial yacht design. First of all, we'll use CFEM to compute the hydrodynamic pressure on the hull, and then we'll move over to what's called RAM series, which is the structural model, structural modeling technique in TDYM. See some of the parameters here: 26 meters long, beam overall 6 meters, draft 2.4 meters, and about 173 metric tons. Okay, so that's strange. That's not how it showed up in my other. Anyway, that says ship computation meshes. The first one up there on the top is for the CFEM, and so now we're only considering what's at or below the water line, and there's no appendages, no rudders, there's no props. And then the second images show the RAM series structural modeling, including the shell plating on the outside, and then some of the ribbing and bulkheads inside the structure. There's no superstructure considered here, just because it provides relatively little strength to the ship, and it simplifies the model quite a bit. And it's just considered as a uniform material throughout. So the hydrodynamic pressure on the hull is shown here. This is for some particular time step during the simulation. This is, I guess this would be a sagging condition. The pressure is about amidships, and so the ship is being deflected at the 2 ends downward. And so this is sort of a typical result that you get out of CFEM during the simulation. So then, taking that information, going straight over to the structural model for RAM series, you can get deformation throughout the ship, as well as the stresses. In this case, this is one we see stresses for all of the shell plating and the interior structure. Okay. So it's a nice package. It is readily available, readily easy process to go from the FSI problem to the structural problem. So now let me talk real briefly about some of the hydroelastic problems. I couldn't go through this presentation without saying the word Elasdyna, because our research group uses that quite a bit. And so that's a nonlinear multiphysics finite element model. In this case, it utilizes an arbitrary Lagrangian Eulerian formulation. As an example of this is a simulation Ravi Chawla has been working on, and I'm trying to validate and verify with experimental data of SCS bow finger seals. I'll describe that a little bit better in a second. The geometry that you're seeing here is the same geometry that I showed early on with the folded up fabric at a free surface. Okay, so now the other way of doing this is using TDYM, again with CFEM and with RAM series, but in this case utilizing weak coupling for each time step. And what's nice about this is that you can just script the 2 programs to communicate back and forth right there in the same TDYM environment. So the hydroelastic example here that I'll be talking about is surface effect seal dynamics. So what is a surface effect ship in the first place? So basically, it's a catamaran with a rubber or some kind of flexible bow seal, flexible, typically rubber stern seal, and those boundaries form an air cushion underneath. So then pressurized air gets pushed down into the middle of this volume here and lifts the whole ship up a little bit, reducing wetted surface, reducing form drag and viscous drag. It's a typical or a design for a high-speed marine vehicle. So now if we use CFEM for this particular problem, and actually this really should say RAM series also, it's a combination of the 2, we can treat this as a towing problem, ship towing. And the structural model uses a membrane elements with the number of nodes listed there in the bow and stern seal. And so when we start at time 0, the geometry of the bow seals looks similar to this. Yeah.
So I have a quick question. So why do the bow and stern seals have to be flexible? If they're rigid, will it not capture the air? Will it not keep the air in?
It does, it does. And in fact, what I'm about to show is a comparison of rigid versus flexible seals. But in operation, it significantly increases the loads on those two areas. And so then they would just get ripped off at high speed. Because these, well, like I'll just show here, this is moving at 1.2 fluid number. It's really moving through the water quite quickly. And then also any kind of wave environment, it helps to conform to that surface. So this is the undeformed geometry for the bow seal. And some of the results here, we have the deformed seal geometry. This is taken again one particular time step. Note that the webbing, this is called the webs of the fingers. The webbings are considered as a rigid constraint in this case, so it's not exactly what we're looking for, but as an example of how this highly deformed geometry can be inferred from the hydrodynamic loading. So for the stern seals, very, very similar. Now these are completely different in that these are 2D objects and not 3D fingers like the bow seals. In this case, this whole region up here is considered rigid, and then only this bottom portion can flex as it impacts the water. And so again, we have deformed geometry and it's moving through the water. So now to get back to the question there, there's significant differences between the rigid and the flexible seals. And in this case, we're looking at just a half-hull view and semi-transparent decks also of a simulation with rigid seals. And this question actually, I think, brings up a lot more questions than answers, but if we just focus on this area right here, you can see that it's relatively a 2D flow in this region coming underneath the bow seals. Even though there is some 3D geometry associated with the rigid seals on this particular ship. Now, if we go to a flexible seal case, now that they're free to move about, you can see now there's a lot of 3D flow in that region. There's other issues with the marine outside of that. We'll just focus on this for now. So, fairly short talk, and again, I don't think I really told anyone what they didn't already know in some cases. But I wanted to try to demonstrate the effectiveness, advantages, functionality of a couple of time domain simulation models. For FSI, we saw we have a rigid body, motions, and nonlinear external forcing through TDXX. And then also we can calculate external pressure on a rigid body and the structural response due to that pressure. With Hydra Elastic problem, we have a highly flexible material, nonlinear deformations, but we can solve that at least through weak coupling with CFUM and RAM series, including the free surface impacts with forward speed. Now, there's some argument as to why LS Dyno might be better at that because it's a better impact contact sort of solution, but at least we have a somewhat reasonable solution from TDYM also. That's it. Any questions? That's not a good sign.
So,
Yeah.
could you send out maybe, or TDXX, is that available on the file
Yeah.
exchange?
It's available on SourceForge.
Just Google it.
You did? Okay, cool.
Does CFEM account for the instantaneous surface of the sea?
Yeah.
Okay, because I saw that, I think that when you had the slide up there, you said that, you know, the panelization is only below the mean surface. I was wondering
Right.
what happened with large waves, or
Right.
with you know, slamming loads, or
Yeah.
does any of that account for it?
It can be. One of the ways you can solve that is the fluid domain has to be at z equals 0 and below, and that's part of the formulation in the software. But you can also import the geometry above the water line to give you some estimation of what happens above z equals 0. That's the way it's been explained to me, yeah. So to this point, I've only used it cut at the water line.
The fluid domain's not defined.
At
By
time equals
zero.
0. At time equals 0.
Oh, okay.
Yeah.
Okay.
Yeah. That's I'm fighting with that problem right now.
Is CFEM public domain, or what's the licensing on?
The CFEM,
Yeah.
no, it's not. We're partly funded through an ONR Global grant, and part of my task is validation verification of that, so that's why we have a license to it.
Okay.
And I knew that question was going to come up, but unfortunately, I don't have a good number for you, for cost-wise at least.
Okay.
So, yeah, I mean, a lot of these codes are linear codes, and is the movement towards nonlinear codes, or is that kind of a secondary market, or?
Well, I mean, I think it depends on your problem. If you're talking about a design cycle type of problem, where you need something on the orders of a couple days, then things like TDXX or Laminate or Aqua are very, very nice solutions, and they're fairly cheap too. But as you get into past conceptual design, into preliminary design, then the structural response starts to matter. Especially if you're dealing with extreme seas where you potentially have very large wave impacts and you need some robust structural members. So it depends on your problem. You know, I think Jim Ray can speak to this quite a bit with Elasticity. It's capturing all of the physics. I mean, everything that you could really reasonably want, but it takes days to do seconds of simulation. Right? CFEM is a little bit faster, and then as you march down, of course, TDXX took 30 seconds. Right? So it depends on your problem, I think. Hope you got something out of it.
Absolutely.
Thank you.
Well, thanks, David.
Yeah.
Appreciate it.